Hello, I think everything's ready. I was fixing a typo in one of the pages. I realized that I saw a typo at the last minute, so I was fixing that. So I was a couple of minutes late. Do you hear me? Everything seem okay?
Yes.
Okay, let me get what I need up. Okay, now the reading assignment for today was to read the chapter on polymorphism. Okay, and we're gonna start talking about polymorphism, but indirectly. Okay, polymorphism is a pretty difficult idea, and it's something that's explained mostly by examples. It's really hard to give definitions of what the word polymorphism means. So what we're going to do is we're going to work on these practice problems a little bit more. We did some of these in class the other day, and there's another list of practice problems real similar. Okay, these are the we did some of these problems here of putting types on these variables. Okay, all of these examples are not polymorphic. And then here are real similar problems. Okay, these are the not polymorphic ones, and these are polymorphic ones. The exercises were, remember, to add types to the second version of each function so that you just explicitly said what the types were. These are all polymorphic. So we'll finish these. And then we'll see how when we transition from these to these, something really changes in ML. There's kind of a big leap from this first group of problems to this second group of problems, even though they're similar kind of problems. And that'll introduce the idea of polymorphism. And then we'll talk about polymorphism kind of in general and give some examples from Java to see, like, how does ML style polymorphism differ from Java style polymorphism? Okay, so let me start by downloading this file. And this one that has a second set of problems. And actually, this one, let's see. Oh, I have a couple. Let's see. I have more than one set of, wait, I'm getting mixed up which set of problems. These are, oh, these were to annotate them. We worked on these the other day in class. Okay. These were the ones to rewrite these guys using pattern matching. That's what we were working on in class. So we did some of these. We took each of these and rewrote them using pattern matching. So what we'll do is we're going to work on these. These are the new problems. We're going to start with these. These can also be rewritten using pattern matching. So what we'll do is we'll do both. We'll put the types on these and see that these can also be rewritten a little bit using pattern matching. Okay, so what we want to do is take these problems and give them types and see if they can be rewritten using pattern matching. And then we want to do these problems, which are similar, but give them polymorphic types. So give these things types and give these things types. Okay. Actually, let's go back to this one too and see what me download the solutions to that one. We did on this one, there's 1, 2, 3, 4, 5, 6 problems. And I think we did the first 3 of them. Okay, let's check. So on the solutions, we did F1, F2. Yeah, we did. Oh, we just did the first 2. So we can do a couple more of these, and then do the ones where we put types. Okay, so let's start with these, practice writing things in patterns, then practice giving them types, and then switch to polymorphic types. Okay, so start with these, which are just writing things in, writing them as patterns. And then this practice, these practice problems. And I think I already downloaded those. Okay, so there's 3 sets of problems here. Okay, don't need that one for now. Okay, all right. So let me open this up in an editor. Okay, so actually, one last thing. Let me download the problems without the solutions in them. Okay, this is the problems without the solutions. Okay, here's the problems without the solutions. Okay, so turn these into problems, turn these into definitions that use patterns. Notice that everything is just f of x, f of x. Okay, this one, it's f of x, but with a type, and just f of x, f of x, f of x. But the x here is all different kinds of x's. So when you write things with patterns, it becomes easier for people to read your functions, and it becomes easier to see what they're doing. Like on this one, we see that you're taking the head of x. So this was actually a list, okay? So like over here, you could write that one, instead of writing it this way, you could write it with a pattern. So you're gonna really add one to the head of the list. So you're gonna write the list as something in front of the rest of the list. And then we use the something, add it to one. So notice instead of calling a function on x, we pattern match x and use the thing that we're interested in. Okay, so instead of calling a function, we can use a pattern match. Now this pattern match can actually be rewritten a slightly better way even. Okay, notice that I never use this because I don't need the rest of the list. So this one can be improved a little bit as, since I'm not using that part, I can use a wildcard there, okay? So then I'm saying the function takes in a list with x at the beginning. I don't really care what's left in the list. And I'm going to just add one to the first item in the list. And that's what I return, okay? Okay, now remember we said that this thing actually has got a little hole in it. This is a function of a list with one item in it. So it doesn't handle a list with no items in it. So then this improved the function to say, well, if you give me a list with nothing in it, I'll give you back 0. And if you give me a list with something in it, I'll add one to the head of the list. Then this one can be written as a pattern this way. F of the empty pattern gives you 0. F of the non-empty pattern adds 1 to the front of the list. And then we could actually rewrite this one using the wildcard. So this one could be said, well, I'm not using that part, so that rewrites it using a wildcard. Okay. And remember, we pointed out that when you define the function this way, the compiler didn't notice that there was something missing in this function, but the compiler knows that there's something missing in those. So for example, if I go over here and I open up the interpreter, I can just type these, I can give these to the interpreter one at a time. This one, the interpreter, see, no problem. Okay. On the other hand, if I give it this one, which is the exact same function, it warns me, you're missing something here. You haven't said what the function should do when it's given an empty list. Okay, so if the function is given an empty list, it gives me an error. Oh, I'm sorry. The function was called f1. That was a different error. The function f1 on an empty list throws an exception. Okay, and so did the first one. See, if I go back to this definition, even though there's no warning, f1 on an empty list throws an exception, but the compiler didn't warn me. Okay, so that's one of the disadvantages of not using pattern matching. The compiler is smarter when you use pattern matching. That's an important feature of the language. The language was really designed around pattern matching. So the compiler ends up being smarter when you do things with pattern matching. Now, this function could be fixed with this, and this one could be fixed with a second pattern. Notice that those two patterns are a lot easier to read than this if statement. Okay, And then F2, again, F of a list, well, F of something, but then you look on the right and you see head of the list, tail, well, you see the head function and the tail function, so you think, oh, this has to be a list, okay? So when you look at that, you see that it has to be a list. And then when you see that you're adding, you see that it has to be a list of integers. See here, again, this had to be a list of integers because we're adding 1 to whatever's in that list. Here we're adding the first number. Now, this is actually giving us the second number of the list because this takes the first number in the list. This gives us the rest of the list. This takes the first thing in the rest of the list, which is the second thing in the list. So this is adding the first and second things in the list, but that's hard to figure out. So we rewrote it as a pattern. The rewriting as a pattern says, give me a list that's got a first item and a second item, and I'll add them together. Okay. Now, again, we weren't using the rest of the list, so that can be simplified a little bit with a wildcard. We didn't really need that part of the list. So that makes it a little bit better. Okay. Now, this function, there's no warning, but it's not actually complete. Okay. The compiler didn't notice when you write it this way that this function F2 doesn't know what to do with a list with one item in it. See? And F2 doesn't know what to do with an empty list either. It just knows what to do with a list of 2 or more items. If you give it a list with 2 or more items, it adds the first 2. Okay, so in a sense, the function's not really well defined. It's got, now it could be that you actually don't mind it being this way. Not all functions are well behaved. The head function itself, if you give it an empty list, it throws an exception. Okay, and the tail function built in, the tail function built into ML, the tail function on an empty list throws an exception. So it is okay for some functions not to be defined on every possible list, because sometimes it just doesn't make sense. The head of an empty list doesn't exist. The tail of an empty list doesn't exist. Okay, so those things are just, you have no choice but to leave those as exceptions. But sometimes, sometimes you should account for all possible lists. Like in these cases, I'm just arbitrarily say that this function on an empty list should just return 0. Okay, I could have returned 1 on the empty list too. 1 here, I'm adding 1 to whatever's the first item in the list. It probably would make sense here more to say, well, if you give me an empty list, I'll give you back 1 because there's nothing to add to 1. So you could even see, that's where sometimes it can be ambiguous how you would complete these functions. This didn't say what to do on an empty list, and it might not be so obvious what you should do on an empty list. I could return 0 or I could return 1. If I'm adding the first item in the list to 1 and there is no first item, why not return 1? Okay, so again, I could say return 1 there. Okay, okay. I could say that the pattern is on an empty list. If you're adding the first item in the list to 1 and there's no first item, then return 1. Okay. Again, sometimes it can be clear what you should do on the empty list. Sometimes it's not clear. And sometimes there's just no good thing to do with the empty list. Like the head function, it would be wrong for head of the empty list to just try to return something like the empty list. That wouldn't make any sense. There's no way in the world to make sense of what head should give you when you say, give me the head means give the first item in the list. If there is no first item in the list, it has to return an error. So you give it an empty list, it has to return an error. Okay. Okay. But it's also interesting that the compiler doesn't notice that this thing has a missing case, but the compiler notices that these have a missing case. So the compiler is smarter when you use patterns. That's the most important thing to remember. The compiler does a better job when you give it patterns. Okay, so let's see. Now, F2, this is tricky to read, head of the tail. You have to realize that you have to think hard to realize that that's really just saying the second item in the list. This clearly says, actually, especially when you get down to here, It clearly says I want the first and second items in a list, and I'm going to add them together. The fact that it's a list comes from here, because that symbol means you're putting things in a list. So this is deconstructing a list. That's why JavaScript calls this deconstructing. You're saying that the input to F is a list, and I want to pull it apart into its first item and its second item. When you use this operator on the right-hand side of an equal, you're building a list. Okay, over here, it's breaking a list in pieces. If you used it over here, you'd be building a list. And that's one of the things that gets a little bit getting used to, is that this is a pattern and this is a value. Okay, over here, we're matching something and we're breaking apart the thing we're matching. So this is saying break something up into its first and second item. If I use the cons operator over here, I would be saying build something. So I would be building a list. And we'll see that in more examples. But you have to kind of keep straight that in the pattern, it's taking something apart. In the value, it's building something up. Okay, same operator has different meanings. It takes apart in a pattern and it builds things up when it builds a value, when it's used on the right-hand side of an equal sign. Okay. Okay. Now you can, like this one. Well, what should you do if the list, we're adding the things in the list? What should we do if the list doesn't have enough things in it? Well, if the list has nothing in it, well, let's return 0. If the list has only one thing in it, now this is a really tricky way to say a list has only one thing in it. To say a list has only one thing in it, you take its tail and it should be empty. Now this is a hard way of saying I want one thing in a list. Okay, this is not the pattern way, this is the hard way. It's saying, well, X is a list, compute its tail. I want the tail to be empty. That means there's only one thing in the list. So I'm going to return the head of the list as the sum of the first two items. Okay. And then if I don't have an empty list and the list doesn't have one item, then the list has two or more items. So then I can safely say, take the head of the list and add to it the head of the tail of the list. And all that's hard to read. And here's the much better way to write it. Okay. Give me the empty list, I'll give you back 0. Give me one item in a list, I'll give you back that item. Give me two items in a list, and I'll give you back the sum of them. Okay. Right. Now, there's multiple ways, like, here's another way to write this one. I'm never using this and this, so I could have used wildcards there. Okay. This one didn't use it, so put a wildcard there. This one didn't use it, so put a wildcard there. Okay. So I'm saying I only need the fact that there's one item in the front of a list, and I'm going to return that item. This is, I need two items at the front of a list, and I'm going to add those two. Now, one item at the front of a list can be written this way. So I can go from here to here using wildcards. But another way to say that the list has exactly one item in it is to write it as a list with one item in it. So I don't even need the wildcard. So I get even a little bit more compact notation, a list with one item in it. And then here I'm using the wildcard. This would be the best way to write the function. It kind of uses the least number of symbols. The empty list pattern, the one item pattern, the two or more item pattern, but be careful. Here's what would be wrong. Here's something that would be wrong to do. The one item pattern, the two item, the empty list pattern, the one item pattern, and then you say, okay, now I go up to the two item pattern. Okay, now my program is broken. My function doesn't do what it's supposed to do. So you see, what's wrong with it now?
Doesn't catch a list with 3 or more.
Yeah, I'm mistaking this thing as the two item pattern. It's the two or more item pattern. See, it's the two or more item pattern. And what I want is the empty list pattern, the one item list pattern, and the two or more list pattern. I don't want to go empty list, one item list, two item list. if I do this, ML is going to complain. I'll show you. If I take this one and give it to ML, it'll warn me that you're missing patterns. See? And it warns me that I don't have enough patterns. I mean, it didn't, that's not a compiler error. That's a compiler warning. It's warning you that the function is not really matching all the patterns it should. So it's going to work fine on a 2-item list. Okay. But if I give it a 3-item list, now that function on a 3-item list blew up because there was no pattern for a 3-item list. The patterns ended with a 2-item list. Now I could add another pattern here, but that'd be kind of silly. I don't need another pattern. I just need to fix this pattern. Okay. I could fix it by doing the following, and that works, but an experienced ML programmer would realize that those patterns are redundant. And I think actually the compiler is going to notice that. I think the compiler, let me see, let's check. No, let's see. Oh, if I'm going to add that clause, I need to get rid of that semicolon. Okay. So the semicolon should be at the very end. You don't put semicolons at the end of the clauses. Okay. So now here's a function. It's kind of got a redundant clause in it. No, the compiler didn't notice. Sometimes it does notice that you have redundant clauses. Okay. Sometimes the compiler can catch that. In this case, it didn't. Okay. So F2 of 3, 4. Okay. And F2 of 3, 4, 5. It's actually treating those as different cases because you gave it 2 different patterns, but they're really redundant patterns. But in this case, the compiler didn't quite detect it. In some places, it will detect redundant patterns. Okay, so, but this would be correct, but silly because it's got redundant patterns. Okay, what's more important is realize that this one is wrong. It's mistaking a 2 or more pattern for a 2 or more list pattern for exactly a 2 list pattern. Okay, so that's not a good idea. Okay, so this one is not good. Okay, that one shouldn't be there. Okay, okay, now let's try one that we didn't do the other day. So those are the ones we did real quick. Was this one F? Now what's interesting is I had to put types in here. Okay. Um, oh, it's got a typo in it. This should be there. Okay. We're supposed to, well, yeah, this is the generic type that we're going to, let's just leave this one off for a while. That's one of the polymorphic types that we're going to talk about in a little while. So this was a polymorphic version of this one, but we haven't said exactly what this means yet. So let's just leave this one aside. So let's look at this one. Okay. Now, what's interesting is, why do I have to put this here? This is saying X is a pair of ints. And this says, take the second item in the pair and take the first item in the pair. Okay. Now, first of all, let's write that as a pattern match. If I write that as a pattern match, I'd say fun F3. Okay. I want the pattern for a pair X. Excuse me. I can write the pattern for a pair as A, comma B. Okay. And I'm going to return B, comma A. Okay. So that's what this is really saying. So if you give me a pair you give me a pair of 2 things, I'm going to give you back the second of them first and the first of them second. So I'm swapping the items in the pair. Okay. Now, what if you got rid of that int there? Why does it need to be there? So let me get rid of it. Okay. So F F3 of something. Okay. Take the second of the something first and take the first of the something second. So it looks like it's that. So it looks like X is a pair. Okay. But the trouble is that's not how ML thinks of it. Okay. If you go over here and you try this one in ML, it'll complain. And it gives you kind of a complicated error message. And here's what it's complaining about. The way ML defines first and second is it doesn't know how big the list is. Okay, how big the pair is, how big the tuple is. This #1 means the first item in a tuple. But there are 2 tuples, 3 tuples, 4 tuples, 5 tuples, 6 tuples, 7 tuples. This guy's not completely defined. This is the first item in a tuple, but ML doesn't know how big the tuple is. This is the second item in a tuple. ML doesn't know how big the tuple is. So this is a tuple. ML knows it's a tuple, but it doesn't know how many fields are in the tuple. So you need to know the names of all the fields in the tuple. Okay. Right now, ML is confused. It knows it's a tuple, but it doesn't know how big it should be. Because of the way %2 and %1 are defined, they're kind of quirky functions. They're actually oddball functions in ML. This takes the first item in a tuple, but ML needs to know ahead of time how big the tuple is. This takes the second item in a tuple, but ML needs to know ahead of time how big the tuple is. And I never said how big the tuple is. So that's why originally this thing said, okay, see, that's what it looked like originally. So this doesn't work. Okay, this one doesn't work. ML is going to complain. It doesn't know how big the tuple is. It gets over to the right-hand side and says, you want the second item in a tuple and you want the first item in a tuple, but you never said how big the tuple is. So here I say it's a tuple of ints. So I'm telling ML X is a tuple of ints. So now it can tell me, okay, I know what the second item is, how to find the second item, and how to find the first item. So this one works. This one works because I told ML that it's a tuple of ints. Okay. And so it's taking in a tuple of ints and give me back a tuple of ints. Okay. Now, for example, I could tell ML, let me go back up to this one, that this is taking in a triple of ints. And what's it going to do? It's going to take in a triple of ints and build up a pair of ints. And it's going to take the first and second, it's going to take the second item out of the triple and combine it with the first item in the triple. So that's okay. It's going to take in a triple of ints and give me back a pair of ints. But I had to tell it how big X was. I have to tell it X is a triple of ints. Okay. And if I want, I don't have to, it doesn't have to be a triple of ints. I could mix the types up a little bit. I could say it's a real, int real char tuple. And what am I going to get back? I'm giving it an int real char tuple, and I'm going to get back a real int tuple. I'm giving it an int real char triple, and I'm going to get back a real int tuple. So I'm giving it an int real char triple and getting back a real int pair. But the key is I had to tell ML how big this thing was. And in the process of telling it how big it is, I told it what types were going in there. So I'm saying that it's an int real char going in. Okay. And then it figures out, okay, you're going to take the second of those three, you're going to take the first of those three and put them in a pair. Okay. But ML needed to be told how big this was. Now let me rewrite this as pattern matching. Okay. So now let me write this in a pattern matching way, because this is really, see, now this is the way to write it in pattern matching. But here's going to be something funny. If I give this to ML, ML is actually going to not give me, okay, what? ML is going to, whoops, I didn't copy it. Right now, ML says, oh, you're taking in a pair and giving back a pair, but notice it's got nothing to do with ints. It's got this, it's actually become something called a polymorphic function. Because from the point of view of ML now, what you're really saying is, give me any pair, and I'll just swap the items in it. It doesn't really have to be a pair of ints. So this is ML's way of saying, what you're really telling me is you're saying this function takes in any pair. That's what the A and B is. The quote A represents any type, and the quote B represents some other type. These are type variables. So this is saying that the function takes in type variables. So the function can take in any type A and any type B, and it gives you out a type B paired with A. Okay. Now that's what we're going to be talking about in the next chapter. Is this is a polymorphic function. Now, if I want, I can make it back to being just about ints. So I can say int pair int. Okay. This one now is that one. Well, this one here. These two now are equivalent. Here I said the input is a pair of ints. And here I said, well, actually here I'm saying that the output is a pair of ints. Okay. Actually, this notation here says that the output is a pair of ints. Okay. But it's saying that these guys are ints. Another way to say that would be, I could say int, that's actually, this one is actually closer to what I started with. This says a pair of ints. This says a pair of ints. This says return a pair of ints. Well, if I'm returning a pair of ints, the inputs must have been a pair of ints also. Okay, so this is returning a pair of ints because the colon's on the outside. Okay, now I've got a function, but notice that this is way easier to read than this one is. So this did not use pattern matching. This just said the input is X, and you're going to give me back, I'm going to give you back the second item from X followed by the first item from X. And this is saying, give me a pair. I'll call the first thing in the pair A, the second thing in the pair B, and I'm going to give you back them in reverse order. Much easier to read than this one. These two are the same. They both, now I've got this guy. Copy it and paste it. See, now I've got it, taking in a pair of ints and give me back a pair of ints. Okay. Okay. Now, remember over here, I was able to throw in, I was able to take this thing and change it to, I made it an int, I can make it an int char real pair. Now the output is a char int pair. So int is an int char real triple, and out is a char int pair. Okay. Now that's without pattern matching. If I write it with pattern matching, that one with pattern matching would be F3 of, well, an A, a B, and a C. And it's going to give me out the B and the A. Okay. Now, if I want it to be like this one, I would put, the easiest way to do it would be to put types on each of this. That's an int char real triple. Okay. So this one, I can go over here and okay, an int char real triple in using pattern matching, and what's coming out is a char int pair. Okay. Okay. Now there's a bunch of ways of typing this one. Let me type it a couple other ways. Suppose I did this. Suppose instead of putting the types on the input, I try to put types on the output. Okay. Well, what am I saying now? I'm saying now that the output is, well, remember it was char int on the output. So I'm saying it's a char int out. But notice that this is kind of, well, I'm sorry, char times int out. There's these two are not equivalent. Does anybody see a little hole? Those two are, this one and this one aren't really the same thing. Why not? Triple going in, pair coming out. There's the pair coming out. The pair coming out is a char int pair. What does that tell me about the input? This char is which of the variables? Okay, it's the first item in the output pair. So that's the B. This is the second item in the output pair. That's the A. What's missing? What did ML do that's clever? See, I never said what C should be. Because if you read this kind of backwards, there's the output pair, char int. So char is B, int is A. So that feeds back into here and what A and B are. C never got typed. So ML said, oh, it could be anything. That's ML's way of saying, well, the C actually can be anything you want. So it takes in an int, char, anything, could be a string, could be a Boolean, because it's going to drop it anyway. So it's not going to show up in the output. So it doesn't matter what its type is. So we say it's polymorphic. We'll see how we use that as we go along. But my type information here did leave a hole in things. Whereas here I said A is int, B is char, C is real. Here because I'm typing the output, not the input, and the output only uses 2 of the 3 variables, I ended up not saying what C should be. And so ML said C can be any type. So the third type in the triple is an int, char, anything, triple. Okay. Right. So I'm playing around with types and annotations. I'm switching from function notation to a pattern notation. But in the case of tuples, you can't, these guys actually should almost never use these things. There's most people tell you that if you're writing ML code and you ever use these things, you're doing something wrong, because you should almost always be using pattern matching on tuples. It's very rare that you really need to use the #1 and #2 and #3 symbol. So it's way better to write this in terms of pattern matching. Okay. But so here the input was just X. That's the thing, but the thing is actually a triple. See, I'm saying it's actually a triple, and then I pull it apart using functions. Over here, I say the input is a triple, and I pull it apart using a pattern. So the pattern pulls it apart. The pattern deconstructs it into an A, a B, and a C, and then I can reassemble it over here whatever way I want to. So again, just like up here, I'm switching from using functions to pull something apart. See, the functions were pulling things apart here, using head and tail. Here, the # functions are pulling things apart. That's not what you want to do. You really want to decompose things with patterns. Okay? So the better way to write this guy is, well, we've done it a couple different ways. This one took in tuples and returned tuples. And then this version took in a triple and returned a tuple. There's without pattern matching, there's with pattern matching. Okay. All right. Now let's see. Let's look at one. We've got a couple more examples here. Function takes in something. Here I see that I'm breaking it up using functions. And I can see from those functions that this thing really is a list. See, I take the tail of it. I take the head of it. Here again, I take the tail of it. And what am I doing? Okay, now this is not easy to read. I'm taking X and I'm going to build a list. See, here I'm building a list. What's the first thing in the list I'm building? The first thing I'm putting in is, well, I take the tail of X, which drops the first item from the list and gives me the rest. Then I take the head of that. Well, the head of the tail is actually the second item in the list. That's what that is. That's the second item in the list. And this is the first item in the list. So I'm taking the second item in the list in front of the first item in the list. Then what have I got here? Well, this drops the first item of the list and gives me the rest of the list. And then this drops the first item of the rest of the list and gives me the rest of the list. That's essentially the dropping two items from X. Okay, so you can shorten this a lot by writing F4 of, what am I doing? I want an A in front of a B in front of a, well, I'm going to use X and Y. I have an X in front of a Y in front of Y's, the rest of the list. I've got two, I need the first item, here I need the second item in the list, here I need the first item in the list, and here's the rest of the list after I've dropped two items. Okay, and what am I returning? I'm returning the second item in the list in front of the first item in the list in front of the rest of the list. Remember, this is breaking it apart. This is putting it back together again. Now I need parentheses on the left-hand side. I need to put a pair of parentheses around there. Otherwise, ML will complain. Okay. So here I'm saying, you give me a list with two or more items in it, and I swap the first two items. Way easier to read than that one. Oh, and fun 4. Okay. That's way easier to read. Okay. So you give me a list with, this is saying you give me a list with two or more items in it and I'll swap the first two, but it's saying it in a really complicated way. You have to really read that carefully to see that you're taking the rest of the list and then the first item in the rest of the list. So that boils down to the first item, the second item in the list, in front of the first item in the list, in front of the, well, what's left after you've taken two items off of the list. And that's what this says. First, the list is a first, a second, and a rest. And then you take the second in front of the first and the rest. Okay. So that's so you end up with a much easier to read thing after you've, oh, and the compiler there's actually a hole in this because this is saying that there has to be at least two items in the list. So this function will blow up if you give it an empty list. Now, so will this. Now, this one, the compiler doesn't notice that. Oh, I'm getting funny copy and pasting. I don't know why. Okay. Control C. Okay. No mention of any problem, even though F4 of a one item list blows up on me. Okay. F4 of a one item list is not well defined. Okay. But when I write it with patterns, I'll get a warning telling me that, you're missing some patterns here. The function, it's only a warning. The function is defined, but I got a warning, you're missing some patterns. The warning is match non-exhaustive. You can't match every possible input to F4. So F4 does not have a way of matching a one item list. So it blows up. F4 doesn't have a way of matching a empty list. So it blows up. Okay. The compiler warned me when I used this notation. Okay. I could fix that. Let's see. So what should F4 do? It's, let's see. So function F4. Okay. Well, what should it do on an empty list? Probably just give us back the empty list. Okay. So yeah, for swapping the first two items in the list, if you give it an empty list, there's nothing to swap. So that kind of makes sense. And then if you give it a one item list, well, you're supposed to be swapping the items in the list. So just give back, there's nothing to swap. So just go ahead and do that. And then there's the case that we're really interested in. If there's two or more items in the list, if there's two or more items in the list, okay, if there are two or more items in the list, then swap the first two. Okay. So there's a reasonable way to fix this function. Yeah, it seems reasonable to say that what this function is trying to do is, since it's swapping the first two items, there's nothing to swap. Okay, so just give back the list you started with. There's nothing to swap, so just give back the list you started with. Or there are two things to swap. Now there might be some situations where somebody really wants it this way. Maybe they want the program to blow up when this function is given a one item list to essentially say that's an error. Maybe they have a sense that this function shouldn't be defined on a one item list or an empty list. ML will let you do that, and then your function could, for example, catch the exception. So if this function is given a short list, a one item list or a zero item list, and you throw an exception, just like in Java, you could catch the exceptions. It raised an exception. They call C++ also uses the phrase, well, throwing and raising exceptions are synonyms. Some languages call it throwing an exception, some languages call it raising an exception. Okay. But it, just like in Java, you can catch the exceptions. So I may want this function to be this way, so I can catch the exception when somebody gives this function a short list, I want to know it. On the other hand, I may think that this is better. Yeah. So, but now the compiler at least warns you. Yeah. So now F4 works fine on empty lists. Oh, no, what did I do wrong here? Oh, that's a different. Yeah. That's a real weird error here. F4 works on an empty list, but I got the right answer, the empty list. But this is one of the really weird bugaboos of ML. This thing called the value restriction. We'll talk about that later. But this function really didn't know what it is it didn't know what kind of list I gave it. I gave it an empty list, but it doesn't know what it's an empty list of. If I say here, oh, that's an empty int list, then it's okay. See, it gave me back an empty int list. Okay, notice the difference. That's just saying I'm giving F4 an empty list, and it does not know what type of list it is. So I can tell it that, oh, it is an empty list of integers. And then ML will complain about this and it won't complain about this. Or I could tell it's an empty list of reals. See? And then it gave me back an empty list of reals. But if I just give it an empty list, it doesn't know what it is. So it warns me that it's giving me back an empty list without knowing what kind of empty list it is. See, it's got this funny type notation, and it's warning me, you gave me an empty list. I don't know what kind of empty list it is. So I'm giving you back an empty list, but I don't know what kind of empty list it is. That's called the value restriction. So I can fix it by saying this weird thing of saying what kind of empty list. Oh, it's an empty care list. I'm giving it an empty care list, so it gives me back an empty care list. Okay, this doesn't happen very often, and it's only a warning. It's not an error. And when it does show up, you basically have to say what kind of empty list you want, which it doesn't come up very often. But when it does come up, it seems annoying, but it's easy to fix. Okay. All right. So this one had holes in it. It's hard to read. Notice there's two problems with this style of writing. One, it's hard to read. Two, the compiler doesn't notice when you have holes in it. This is much better, easier to read, and the compiler will warn you that you're maybe missing some patterns. Okay? Okay, let's do one last one here. Okay? X is something. Okay? Well, what is it? Well, since I'm taking the tail of it, must be a list. Okay? Head of the tail of it. Oh, I'm adding these things, so it must be a list of integers. Okay, now what am I doing? Well, this is kind of tricky to figure out. See, well, here's where I'm building something. What am I building? I'm building on the tail of X. So that means I've taken off two items from X, because the tail of X, I have to remind myself that means remove one item from X, remove another item from X. So this is the rest of the, after two items have been removed. So here's what I'm putting in front of that. What I'm putting in front of that is, well, the head of the tail of X is the second item added to the first item. So what I'm doing is I'm taking a list of two or more items, adding the first two items together and putting them back onto the list. Okay, so what I'm doing, I can go over here and I can play around with that. Okay, it's F5 will take a list of two or more items, and it's going to take the first two items, add them together, and put them back on the list. So it took 1 + 2 is 3 and put 3 back at the front of the list. You know, if I do this, okay, so it took 5 and 3 off the front of the list, add them together, and put it back at the front of the list. Okay, I can write that in a way more readable way with a pattern match. Okay, fun F5 of, well, now I need an X in front of a Y in front of the rest of the list. Oh, but I'm not gonna, I'm gonna see, I don't really even need, oh yeah, I do need it. Yeah, I need to know, I have to give it a name. Okay, I'm not going to do much with it other than put things back in front of it, but I do need to give it a name so I can put things back in front of it. So I need an X, a Y in front of the rest of the list, and then I'm going to take X plus Y and put it in front of the rest of the list. Okay, right? And that's the easier way to write this. But notice that the compiler again warned me that, you know, you're not taking care of every possibility. You know, you're not saying what to do with a 1-item list or a 0-item list. Okay, so I can fix that real quickly because it kind of makes sense what to do. It's similar to the first one, fun F5 of an empty list. Well, if I'm supposed to take the first two items of the list and add them together and return their result back on the list, well, actually, yeah, just return the empty list. That's like taking the first two items in the list and adding them together. Well, they're not there. So when they're not there, they're nothing to add. See, the funny thing is, if you add things that aren't there, you could say you get 0. So maybe you should say, oh, you should return 0. But I think it'd be better to just say return the empty list. Sometimes it can be tricky to say, if you're saying take the first two items in the list and add them, you really, maybe the empty list case, I shouldn't do it. Now, the 1-item case makes more sense. The 1-item case, F5 of 1-item list, well, I'll just return that 1-item list. Okay, that makes a little bit more sense. And then the last case, which is the F5 of, now I have to switch to real pattern map. I have to switch to the constructor version. An X in front of a Y in front of the rest of the list is the X plus the Y added to the rest of the list. Okay, somebody can quibble and say, I don't like these two. They might say, I really think this is better. You shouldn't say what this function does in these two cases. Leave it like this, and it's an error to call this function with a 1-item list or an empty list. And then you catch the error with the exception. So, you can, now the compiler doesn't even warn you about that here. It warns you about that here, but you can just take it as a warning and leave it the way it is. Or you could fix it, but then somebody might quibble with you about how you fixed it. Is that really what you should do on an empty list? Is that really what you should do on a one item list? Okay, but that does fix it. Now the function won't complain. Now ML won't complain. See, the function is defined for all possible lists now. It is defined for the empty list and it is defined for a one item list. Okay. All right. Now, oh, and this was an example of something you can't do with pattern matching. You take in something and you either square it or cube it, depending on whether the number is negative or positive. That's not a pattern. That's a condition on the variable. In more modern languages, ML is still not the most up-to-date language out there. This is handled in more modern languages with things called guards. That's not a pattern, that's a guard. And in Haskell and Clojure and Scala, you can do this with patterns, but you have to combine patterns and guards. So then you do it in a more modern language, you have patterns and guards. So you don't need to write an if statement. You can write this in Haskell real elegantly, but you need a feature that ML didn't think of, which was putting guards on patterns. Okay, so in ML, you're forced to write this as an if statement. You have to write it as an if statement. If X is negative, then there's this case, else this case. Okay. All right. So you're kind of this is one of the few things, this is something that can't be handled by a pattern. It's really a condition on the value, not a condition on the structure of the value. It's a condition on the value of the value, not the structure, but see, these are conditions on the structure of the list. Is it a one item list, a two item list, or three item list? It wasn't a condition on, is the first item in the list a positive number? If I was to do something where the first item in the list is a positive number, I do one thing. If the first item in the list is a negative number, I do another thing. I can't do that with patterns. I need an if statement. Because then I'm not saying it depends on the structure of the list. I'm saying it depends on the value in the list. So, but it turns out structural things are more common than structural things like this turn out to be way more common. Is it an empty list, a one item list, or a two or more item list? That's more common than saying things like, is the first item in the list a negative number, or is the first item in the list a positive number? It turns out that structural things turn out to be much more common in programming than things like this would be. These kind of things tend to be buried inside functions. So you're more likely to use an if thing deep inside of a function after you've done pattern matching. So in ML, you're more likely to see this kind of if statements inside of the body of the function after you've pattern matched. Okay. All right. Now let's go and do some of these other examples that are. What we've done is we've finished these examples where we've written things with pattern matching. Now let's go look at practices with just typing information. Okay. Just typing information. I want to annotate this function with what its types are. So I want to do what the ML compiler does. The ML compiler figures out what the type of everything is here. There's no pattern here. What this is really doing is it's taking in, I'm adding one. Okay, now addition takes two reals or two ints. That's an int. So this must be an int. So I annotate that by saying that X is an int. Okay. Now the function then takes X and adds one to it and returns an int. Okay. Now let me type this three different ways. Okay. Let me do three different things here. I can say that this is a function that takes in an int. I can say that this is a function that returns an int. I can say this is a function that takes in an int and returns an int. Now, ML will figure out you can just give this to ML, it figures it all out for you. Here I'm adding the type information step by step. Here I'm saying the input is an int. Here I'm saying that the output is an int. And here I'm saying both, that this is the Java-like way. It takes in an int and it returns an int, which is exactly what ML figured out over here. What's quirky here is this one looks like you're saying that the input's an int, and it's got to be careful. That's not the case. The way this one is grouped like that. Okay, so I could actually put in another case here. And this is, yeah, that middle one is grouped as if it was like this. So this one is actually the X, the type is on the return value. That's why, see here, I grouped it where the type is on X, is on, see, but the parentheses mean it's the input value, that the int is, yeah, so X is in and the type is on the input. Okay, this is in, but the way ML, this is bound to this guy, so then it's saying, okay, that's its input, so then then this is the output. So the output is int. Okay, and then this, again, see, this makes the grouping clear. Okay, so the type is on the output. And this is here, type on the input, type on the output. Okay, now here's how you can see that this was really typing on the output. If I go over here to ML, okay, okay. Now, right now I don't know if that was typing the input or the output because the function went from int to int. Okay, now let's see if this tells me. Let me think. Let me just change the function a little bit. Okay. Now look at this right-hand side. Look at it real carefully. What is X? What's the type of X? What does the real function take in? This is like a cast. It takes an int in and gives me back a real number. So it converts an int to a real, then adds a real to it. So this is adding, so this is taking in an int and giving me back a real. Okay. Now notice, see, that colon real was the return type. It was not saying that X is an int. It's not saying that X is a real because X is an int. See, unfortunately, this is one place where ML's syntax is a little bit hard to read. It looks like I'm saying that X is a real here, but no, that colon is on the return type. And I can see that X is an int, okay? So if I wanted to type that completely, I would say that X is an int. Oops. X is an int, and the function returns a real. See, so it's see, X is an int, and it returns a real. But you got to be real careful. See, when you write it like that, it'd be real easy to think that means X is a real. Okay, but the grouping is that that's the return type of the function, and the ML figures out that the return type is real for sure, but the input is an int because of that guy there. Okay, so this one, you gotta be whoops. This one's gotta be, you gotta be real careful with this one. And put, you gotta be real careful with that one because it looks like I'm typing the input, but I'm really typing the output. Okay, so here, that's typing the return type. That's typing the return type. That's what it means to type the input type and the return type. Okay, now let's look at some other examples. Okay, what is X here? Well, I'm taking X, and just like we did a minute ago, I'm converting it to, so it's this similar example here. I'm taking X, it's an int, so X is an int, but I have to be careful. That X is an int, so I have to group it like this. But then I take that int, convert it to a real, and so it, just like the example we did a minute ago, it returns a real. Okay. Right. So that's essentially, I mean, it's this example here, but it's this example here, but it's showing you that you got to be real careful about how you read that. So you wouldn't write this one that way. You wouldn't, if you, well, these are all equivalent now. See, that's correct, but you got to be real careful. Yeah, you kind of would want to write it like that. See, because that's really saying that the return type is real. That's not attached to that X. Okay, but you can do it like this and make it look like it's attached to that X, but it shouldn't be. It should be over there. And then you could actually type it carefully. Okay. Now, so let's go to this one. What does this one do? Okay. We want to say what the type of X is, what the type of Y is, and what the return type is. So let's go over here and ask, let's think like ML does. Now, we're supposed to do it on the second one so that you can compare the types of these two if you run it through ML. Okay. X is put into the round function. The round function takes in a real number and converts it to an int. So X would be a real number. Okay, so let me group it. So I'm saying X is a real number because it's the input to the round function. Now the round function gives me back an integer. So that gets added to Y. So Y is an integer. And I group it like that. Okay. Now I've taken a real. I'm taking a real, rounded to an int, adding it to an int. So this is an int. Oh, but then I say take that int and convert it back to a real. So the output type is going to be real. Okay. Now what we want to do is check that we did that right. So take this version and give it to ML. Then take this version, give it to ML, and make sure that we didn't change the type. Now, here I can check. What's H1? H1 is that type. H2 is that type. See, I didn't change the type. I did H2 right. I typed it correctly because I can see I got the same types. Okay, so here's how I would explicitly type that function myself. Now, ML will type it for you. What's the purpose of a problem like this? If ML will type it, why should I type it? And the answer is, in the real world of ML programming, there's two schools of thought. One school of thought says, write your functions like that and let ML figure out what they are. One school of thought says, no, you may not, what ML type, the type ML gives it may not be the type you think it is. You should say what you think it is, and then let's see if ML agrees with you. You should say what the type is and make sure that what you say it is what ML figures out it is. So here I'm saying on the left-hand side what I think the function is doing, just like in Java. H2 takes in a real and an int and returns a real. So very Java-like. And then I'm, okay, if ML thinks differently, I'll get a compiler error. If ML looks at this right-hand side and says, nope, that doesn't agree with this, I get a compiler error. And that might be a better thing. Instead of me thinking it does this, when it really does something different, that can be an error in my code that might be hard to detect. So one school of ML programming says, always type your functions and let the compiler verify them for you. Another school just says, let the compiler do all the work. I think in places that really do ML programming, they mostly use this second style. They want the compiler to help them, not to do their work for them. So the type inference of the compiler is really there to help you, not to really do work for you. So don't write JavaScript-like code. See, this is JavaScript-like, this is Java-like. In JavaScript, you don't write any types, but JavaScript has a lot of problems with that. This is Java-like. I'm putting all the types in there. Well, ML says do both. Put in all the types and then let the compiler verify that what you did over here really matches what you said it was. Then you kind of know that your program's doing what you think it's doing, okay? And also, what's the purpose of this? It makes you think about ML, okay? It makes you read these things real carefully. So an exercise like this is a good practice in reading ML carefully. So let's do another one, okay? What's X and what's Y and what's the return type? X is concatenated to something. Well, the concatenation operator takes in a string on the left. So X is well, I'll do it on the next one. X is a string. That's its input. That's an input type. So X is a string. Now look what's here. Now the right-hand side of this is a string also, but in the integer class, I call the toString method on Y. So that means that I'm stringifying an integer. So Y is an int. So Y is an int. Okay. Now I put the return type on the last parameter. See, you don't put a return type here. You put the return type on the last of the parameters. See, I didn't put a return type on this guy. I put a return type on the last of the parameters. Okay, so here's where I'll put the return type. The return type is string. So the function takes in a string and an int and gives me back a string. And then I can check that I did it right by going over here. There's, whoops. Oh yeah, those were, it loaded that class for me. See, so it's just like Java. Java does the same thing. When you kind of like, it did an auto importing or auto loading. So I won't see that again. So if I do it again, see, I won't see it again. So it loaded it one time. Okay. And then check that this thing, does it give it the same type? Okay. K1, K2. See, I typed it right. K1 and K2 have the same type. So I typed it right. Okay. All right. Now, if you go through the rest of these lists, like, let's do real quick this one. What's X and Y? Well, that doesn't tell you anything. Addition can take in 2 reals or 2 ints. So you don't know what that is. Okay. Go over here. Oh, well, multiplication could take in 2 reals or 2 ints. Doesn't tell you anything. Ah, but this guy tells you something. The input to real is an int. Okay. So real converts ints to reals. So that means the output of this is an int. So that means that both X and Y had to be int. So now I know that X is an int. X is an int. Y is an int. But the whole thing is returning a real. Okay. Well, no, what's it returning? I'm sorry. No, be more careful. What's it returning? It's returning a pair. So it's returning a pair. Okay. The first thing in the pair is the sum of the two inputs, but the sum of 2 ints is an int. So it's returning a pair with an int, and but then here the product of 2 ints is an int, but then I convert it to a real. Okay, so that was a trickier one because the return value was a pair, and the types in the pair don't match. So let's just check it. There's P1. There's P2. P1 type, P2 type. See, I matched them. Int, an int, and you got to read this real carefully. An int and an int in, and a pair int real out. One integer in, another integer in, and then a pair int real out. Okay, an integer in and an integer in and an int real pair out. And if I want to, I could make that maybe a little easier to read by grouping that as a int real pair, but the parentheses don't need to be there. You maybe want to put them there for readability, but they don't need to be there. This operator has higher precedence than the parentheses need to, than this operator. Notice that this is not multiplication. One of the reasons I gave you this, that and that don't mean the same thing. That's multiplication. That's the constructor of a pair. That's saying I'm returning a pair type that's int and real. Okay. All right. So on Thursday, we'll finish these and start the next group of them, the one that are polymorphic. These are all what's called monomorphic. The function takes in, it takes in just exactly int, and gives me back an int real. There's no variation on the type here. The function is very rigid. This is what Java is like. On Thursday, we'll look at these other examples that are polymorphic, that the function actually takes in a variety of types. Okay, the poly means many. So we'll see functions that somehow switch from being monomorphic to polymorphic. Okay, and that's a big jump in the language. That's a big, that's why we're doing these. That's one reason why we're doing these examples in so much detail. We do these real carefully, do all of these real carefully, and then when we switch to the harder ones, we can kind of see what's going on, that this thing's all of a sudden switching to being much more, when you look at these functions, their type are way more interesting. Oh, boy, my cut and paste is acting really weird. See, it's got these funny type variables in it. Type variables in the answer, those are polymorphic types. That's what we want to learn how to read this. And we learn how to read it by writing it ourselves. We'll type these things, and by typing them ourselves, we'll get a sense of how to read a polymorphic type like that. Okay, so that's where we'll quit. We'll start on Wednesday. Well, on Thursday, we'll finish the ones we haven't done here. We'll finish these monomorphic types, then switch to the polymorphic types, and just get practice with reading ML and writing ML signatures. We're writing ML signatures. We're reading ML code and writing ML signatures. Okay. Okay. Any question about what we did? Any questions so far? Read the chapter on polymorphism. It's very well written. Polymorphism is a tough topic. I think the book does a really nice job of explaining polymorphism about as well as I've seen it explained in most any book. So it's a hugely important topic that's very tricky to explain. And the first thing the author says is, don't expect a definition of polymorphism. You notice that that's the first thing he kind of says in the chapters. Don't expect a definition of polymorphism. It's just too complicated to give a definition. So he gives you lots of examples of polymorphism. And that's pretty much the best way to approach it, is lots of examples of what polymorphism looks like without ever saying exactly what it is. Okay, so we'll quit there. And if you got questions on the homework, remember you have one programming assignment out right now. If you have questions on it, come to office hours or send me an email. Okay, it's due a week from today. So if you have questions about that, let me know. And on Thursday, we'll switch from monomorphic types to polymorphic types. And then we'll see how ML compares to Java and C and languages like that. Okay, so let me stop sharing, and we'll meet again on Thursday. Bye-bye.